So, hello all. Thank you for being here. Special thanks to Aileen, Andres, and the rest of the organizers for this opportunity and all the arrangements. My name is Joel. I am representing the UNOSA Industrial Chair, which is a partnership between the UNOSA Energy Company and the University of Oviedo. Today I will be speaking about our experimentation in numerical analysis of thermal interference in a simulated two-well geothermal system. First, I'd like to ask the room a quick question, and it is, how many of you do know my friend Hector? Hector here is a thunderstorm that occurs precisely at 3 p.m. From September to March in the Tiwi Islands in the land down under. This has nothing to do with the presentation, because what I'm going to be explaining is what was our objective, why we did this. Then I will get to how we did this, our methodology. Finally, of course, results, weaknesses, and the most interesting part, which will be the future research. First of all, our objective, our final objective, because this will be a series of experiments, is to model a real mine, abandoned mine water, a flooded mine, an abandoned flooded mine. So we wanted to have both a physical model, which is shown here, a physical model where we can simulate in a laboratory environment these control parameters like flow, temperature, heat consumption, and we will also have a software model. So this model here, it's much bigger than it seems. It's taller than me, and it has a considerable length. It is filled here with sand, a porous and homogeneous material. And we can run some simulations here. We can gather all the data and compare it to the software model. So here you can see it has an abstraction well, it has a heat exchanger reinjection well. The software we use is called FIFLOW. It is a groundwater modeling software. So the premise of the experiment is to have the same initial parameters, run simulations on one side, take data on the other side, and compare both of them. So how we did this, as with any numerical method, we started creating a model. We have a custom 2D model using the Bang-Nuchen parameters. Here you can see the interest points and some extra interest points around the wells. Then we do the meshing and apply the boundary conditions. Here you can see again the interest points, and the colors just represent hydraulic head, because the first experiment, the first software simulation, it's a 2D steady state simulation of the hydraulic head using the Paradiso solver. With this simulation, we then expand onto a transient 2D temperature simulation using the previous results. And here you can see the result where both wells can be appreciated. So what we do next, we expand into a 3D model. Here is again the hydraulic head steady state simulation. And then we do the transient temperature simulation. Here we can see a longitudinal section where we can again see both of the wells in action. What were our results? Both the hydraulic head and the temperature simulations were great. We are happy with that. We had our weaknesses, chiefly that the pumping radius could not be measured because we did not have access to that part of the physical model. We did estimate it, although as previously said, it did not impact or not in a meaningful way the results. And also that TM flow equation is not applicable in critical zones, which is not a novelty. What is our future research, which I believe, as I said previously said, this is the most interesting part. We want to introduce hollow tubes into the physical model, gather data again, then run the simulations, check, maybe then get some tubes with heterogeneous material, simulate different cavities, mine situations, and getting closer and closer to the real ones until finally we get the most accurate simulation possible, having not only the software models, but also the physical part to bridge that gap. Thank you all. Have a nice symposium.